Now let's continue our discussion on the solution of the linear homogeneous recurrence relations, particularly those which have the degree of 2. But this is a special case where the roots are repeated. Now what I mean by that, let me explain that more formally. Let's say C1 and C2 are two real numbers. So both of them belong to real numbers, and at the same time C2 is not equal to 0, and we'll utilize them in a recurrence relation and in the characteristic equation. So the characteristic equation that we have is, let's say, r square minus C1 r minus C2 is equal to 0. So this is the characteristic equation. And let's say we have repeated roots. So instead of obtaining two roots, r1 and r2, let's assume that both of the values are same. Let's call that r0 and r0. So r1 and r2 both are equal to r0. These are the values that we obtained. Then the sequence, then according to this, the sequence an is a solution to the recurrence relation, is a solution to a recurrence relation an is equal to C1 times an minus 1 plus C2 times an minus 2. If and only if, so all of this is true if and only if an, the solution, is equal to alpha 1 times r0 raised power n plus alpha 2 times n. So this is the addition, this is the one that differentiates it from the equation that we discussed previously, times r0n. So previously, when we had different roots, when we had r1 and r2, and if both of them were not similar, then the solution, the equation that represents the solution, was equal to an is equal to alpha 1 times r1 raised power n plus alpha 2 times r2 raised power n. Now this is something new. So this will be the solution, and alpha 1 and alpha 2 are constants. So this and this both are constants, and n can be 0 or 1 or 2 and so on. Now the meaning of this will be clear with an example. Solution of the recurrence relation where roots are repeated, and the moment we see the repetition, we'll be using this in the equation with the degree 2. So we have to find the solution of an is equal to 6 times an minus 1 minus 9 times an minus 2, and the initial condition will be given. A0 is equal to 1 and A1 is equal to 6. So using these, we build upon the relations, especially when we have to find a series, just like Fibonacci series and so on. Now in this case, we are, for instance, interested in the solution. Therefore, the first thing that we'll do is we'll replace it with the characteristic equation. So the characteristic equation will be r square minus 6r plus 9 is equal to 0. Now if we can clearly see that this is a quadratic equation, therefore by using minus b plus minus under root b square minus 4ac by 2a, since the format is of the form of ax square plus bx plus c is equal to 0. Therefore, the roots that we obtain in this case are 2 and both are similar, and therefore we'll call that R0. Since they are similar, and after calculation we'll find that both of those values are 3, then this can be rewritten in terms of this equation. The solution can be written in terms of this equation. So an is equal to alpha 1 times 3 raised power n, so r0 raised power n, plus alpha 2 times n times r0 raised power n, again 3 raised power n. Now alpha 1 and alpha 2 is unknown to us, and in that case the initial conditions can be helpful. So alpha 0 is given to us, that's equal to, the A0 is given to us and its value is equal to 1 in the initial condition, and A1 is equal to 6. So both of them will be helpful in obtaining the alpha 1 and alpha 2. Now first let's try to find alpha 0 using this equation. An using this equation. So what we'll get is A0 is equal to alpha 1 3 raised power 0, since n in this case is 0, plus alpha 2 0 3 raised power 0. So we know anything raised power 0 is 1, so this will be alpha 1, plus anything multiplied by 0 is 0, so this will be 0. So what we'll get is A0 is equal to alpha 1, and A0 is provided to us already, which is 1. So alpha 1 is equal to 1. And let's move further. Let's try to find alpha A1. So in this case n is 1, therefore that will be equal to alpha 1 times 3 raised power 1 plus alpha 2 times 1 times 3 raised power 1. So A1 is equal to alpha 1 times 3 plus alpha 2 times 3. We know that A1, which is given to us in the initial condition, is equal to 6. We know this is equal to 6. So 6 is equal to alpha 1 times 3 plus alpha 2 times 3. And at the same time, we derived the value of alpha 1, which is equal to 1. So 6 is equal to 1 times 3 plus alpha 2 times 3. So 6 is equal to 3 plus alpha 2, 3. And if you rearrange this, you will get alpha 2 times 3 is equal to 6 minus 3. So alpha 2 times 3 is equal to 3. Alpha 2 is equal to 1. So we found the values of alpha 1 and alpha 2. Therefore, we can use them in the general equation that represents the solution, which is an is equal to alpha 1 times 3 raised power n plus alpha 2 times n times 3 raised power n. So we know alpha 1, we know alpha 2, both are equal to 1. Therefore, this equation will be equal to an is equal to 1 times 3 raised power n. So this will be 3 raised power n plus 1 times n times 3 raised power n. This will be n times 3 raised power n. So this is the solution of the recurrence relation an is equal to 6n minus 1 minus 9 times an minus 2. So this was the example where the roots were repeated. Now that was all about the solution of the linear homogeneous recurrence relations.